Hello, and welcome to the TechBits YouTube channel. In this video, we are going to be taking a look at Postgres table indexing, but we're going to be reviewing the Postgres query performance that we worked on a previous video. That said, let's take a look at where we were looking before. By utilizing table indexing in PostgreSQL, we found out that we have multiple advantages or key reasons to utilize table indexing. We can see we have faster data retrieval, improved query performance, sorting and ordering, join optimization, and we also have constraint enforcement, full-text search, aggregation and grouping, data integrity, and consistency at last. Now, since we have already discussed these details about the key reasons for utilizing table indexing in a previous video, the link to that video is in the description. We will head straight directly into adding data to the previously created database and table. But before we go there, we're going to be talking about a little bit what explain is. These are the terms that we're going to be looking into in the demo. In PostgreSQL, the explain command is used to analyze and display the execution plan of a query. The execution plan outlines how the database engine will process the query, including the sequence of operations, the order in which tables are accessed, and the methods used to retrieve and join data. This information is crucial for optimizing query performance and understanding how the database engine interacts with the underlying table and index. Then we move into another term, which is query plan. A PostgreSQL query plan is a strategy devised by the database system to efficiently execute a given SQL query. It outlines a sequence of actions like table accesses, join methods, index usage, and filtering that PostgreSQL will undertake to retrieve or modify the data. The primary aim is to minimize execution costs, such as disk I/O and CPU usage. Query plans can be examined, use tools like the explain statement of aiding database optimization efforts for better experience and performance. In the context of PostgreSQL's query execution plans, Bitmap Heap scan and Bitmap index scan are terms related to specific operations used to retrieve data from the tables and indexes efficiently. Okay, so now let's take a look at the Bitmap heap scan, its definition. A Bitmap heap scan is a follow-up operation that takes the results of a Bitmap index scan and retrieves the actual rows from the table, from the heap. The bitmap generated during the index scan is used as a set of pointers to the locations of the rows in the table. The bitmap heap scan involves reading the rows directly from the table, which might not be in the same physical order as the bitmap. This operation can be more efficient than a regular table scan when dealing with complex queries involving multiple conditions and large items. Then we talk about the bitmap index scan. A bitmap index scan is an operation that utilizes bitmap indexes to retrieve rows from the table. Bitmap indexes are data structures that map each distinct value in a column to a bitmap, which is a binary representation of the rows that contain that value. When a query involves multiple conditions that can be satisfied by bitmap indexes, PostgreSQL can combine these indexes using bitwise operations to create a combined bitmap that represents the rows matching all the conditions. This combined bitmap is then used to identify the specific rows in the table that meet the query criteria. Okay, now that we have a better understanding of these terms, let's dive ahead and straight into our demo. Okay, so let's go ahead and log into psql. We can see that we are using version 13. And the first thing, let's create a database. Create database my table indexing. It was created successfully. Now let's connect to it. \c connect the database. I am currently connected. I'm going to create the sample table. It has the structure that we already can see there, and now we're going to start following and creating indexes. First one is on the last name. Second one is on the age. And then we have another partial index, an expression index, And here comes the fun part. We're going to populate data into the table. Let's go ahead and count to see if the data has actually been populated in this table. And we have 10,000 counts. That's pretty decent. Okay, let's first take a look at this first explain. We're going to execute the explain along with a select from employees where the age is greater than 30. We see that it is a sequence scan for an employee with a cost from 0 to 112.80, how many rows actually matched along with the width of them, and the filter. What does this mean? This means that it is expected to retrieve 77,249 rows with a row of 44 bytes. The cost of this operation is estimated to be between 0 and 112.80. That's what it really means. Now, on the filter, it means that the filtering condition for this query involves checking whether the age column is greater than 30. In this case, similar to the other queries that we might find out later on, the decision might be influenced by similar factors such as data distribution, table size, available indexes, and query statistics. If performance optimization is a priority, you might want to consider creating an index on the age column. An index on the age column could potentially improve the speed of queries that involve filtering based on age, as it would allow PostgreSQL to efficiently locate the relevant rows without scanning the entire table. Okay, that's for the first one. Now let's go ahead and revert the query and do it so the age is less than 30. We see that this is a top level operation and there is a bitmap index scan in there. This step involves a bitmap index scan on the index named index less than 30. So we can see here, the cost of this index scan is estimated to be between 0 and 32 and 23.23. It's expected to retrieve 2389 rows and a width of 0. So we are seeing various degrees in changes in here with these query plans. Let's check the next one. We see that we have a query here, the costs, the rows, 50 and the width. All of those have changed. Notice, it decided to do a sequential scan of the entire employees table and apply the filter condition during the scan. This decision might be influenced by factors such as data distribution, table size, available indexes, and query statistics. Now that we've taken some time to look at these indexes and how they perform, you definitely can have other considerations. As mentioned before, maybe adding an index to a specific column that might help improve the performance. Remember, indexing and modeling and trying to query performance tuned queries is more an art than a science. So there's no straight answer for anything or everything, but there's many considerations that you can take into account. We just quickly reviewed some of these, and hopefully this will come in handy for you in the future. Feel free to reach out if you have any questions or comments on the video today, and see you in the next ones.